All right, welcome to class. Matt is out of town this week. Not sure where. I think he should be back next Monday, I believe. So my name's Kevin. I work with Matt at his company. So I'll be filling in a bit. First of all, are there any questions about the homework? Is the homework still, or are you guys in your final projects now? Final projects? All right, so assume you guys, your questions for those are more specific. So if you have questions about the final project, come talk to me after class. I may or may not be able to help. Just a note, late days are not usable on the final project. So just keep that in mind. Yeah, great. So I believe you guys talked about a little bit about OpenGL last lecture, I think. Great. So how comfortable are you guys with OpenGL? Not at all? Do you understand basically what it is? Can anyone describe at a high level what OpenGL is? Graphics engine. Great. And OpenGL is also hardware accelerated, so it uses the GPU to distribute all your work across many little individual cores on the GPU. So in OpenGL, this is how we broke it down. The parts that you write the vertex shader, the fragment shader, and the program. And you pass in uniform variables or attribute arrays. And then the top three, the UI window, the root view controller, the GLKit view controller, and the GLK view, those are the tools that Apple provides to allow you to use OpenGL on iOS. Does everyone remember what the difference between a vertex shader and a fragment shader? Can anyone tell me what a vertex is? Anyone? Just a point? Close. So a vertex, your geometry is defined by a series of points, but it's not just a point. There are oftentimes additional information with each vertex or each point. A lot of times this is normal information, for example, which way your triangle is facing, the normals. Is that clear about normals? Normals, you have a triangle. Which way does your triangle face? You could have a triangle facing outwards or inwards. Hopefully your shape, you have all the triangles facing outwards. And those normal values are defined per vertex. So there's additional information, but primarily for this context, it's generally just the point that defines your geometry. So a triangle is made up of 3 vertices. Yes? What about a fragment shader or fragment? Does anyone know what a fragment is in the context of OpenGL? All right, so you have a shape, for example, a triangle. And as you draw the triangle, as it's composited to screen, you do work on, it represents oftentimes individual pixels. So your triangle is a shape defined by 3 vertices, and when it's drawn to screen, it's drawn to hundreds, thousands of pixels, depending on how big that shape is. And so the fragment represents each individual pixel. It is not, in fact, each individual pixel. It depends on how you build it up. Oftentimes, a fragment, it just represents one component as it's drawn to screen. And sometimes the same pixel will be drawn by multiple fragments, or fragment shaders. Okay. So these vertex shaders and these fragment shaders are compiled at runtime down to a program, and this program is then uploaded to the GPU. And the GPU runs that program, and then you pass in the purple values, the uniform variables and the attribute arrays. And that's the information that you use passed to the GPU, which will then perform all the calculations that draw it to the screen. Is that clear, I hope? Right, so this is the OpenGL pipeline. You pass in your raw data. It goes through some processing, goes to the vertex shader, which transforms those individual points or those normals or whatever. So it's readable by the OpenGL system, the rasterizer. It's passed to the rasterizer, which then takes that information and then passes it back to you, to your fragment shader, which then you perform work on each individual fragment. And then all those results are composited down to one final image in the end. Yes?
What is the rasterization?
Rasterization is the process of turning something to an image. So the rasterizer just takes that, it essentially takes your 3D geometry and flattens it down to an image that is then displayed on screen. Because OpenGL displays information in 2D, even if it represents a 3D image. So that's what it does. So your components that you put in are the input data. Then you write a vertex shader. You're writing a program that is run on the GPU. And you're writing the fragment shader, also run on the GPU. All right? And I think the rest of this is just, okay, here's an example of a program. This right here is the vertex shader. All it does is pass in, it takes in an X and Y position, passes it back with a 0Z position and a 1Y position. And this is the fragment shader that just forwards on the color of green, looks like. So very, very simple programs, and this is run by the GPU. It's an example of passing in a uniform. We'll go through this in the example. So I think Matt will have to explain these slides. I'm not sure. Barycentric coordinates are useful to know. Essentially, you can represent a single point on this line, P, based on these lambda values, or the barycentric coordinates. The barycentric coordinates add up to 1, and the way I think of it is it's a kind of a percentage, whereas this P is a certain percentage of A, a certain percentage of B, and a certain percentage of C. And those combine to represent the position P somewhere within the triangle, but not actually one of the vertices or on one of the edges. This will be more relevant probably next lecture. It represents exactly 1 point, depending on your granularity of your lambda values, your barycentric coordinates. But you can represent every single point position within that triangle using these barycentric coordinates. And so the barycentric coordinates are what used to interpolate the values. Essentially, you have 3 vertices in a triangle, but you have multiple fragments. So you have thousands of fragments. They're performing these calculations to pass you a certain fragment, and it will interpolate certain values so that they're appropriate for individual fragments, not at the vertices. Kind of interesting. Probably not incredibly relevant for today's lecture. And I think the rest of these slides, Matt will have to go more into detail about. I believe it's just calculation. Okay, great. Here's an example. So we have point A represented by blue, point B represented by green, point C represented by red. And barycentric coordinates are used to interpolate those red, green, blue values. So at this very specific position, there's a certain percentage of blue, a certain percentage of red, a certain percentage of green. And that interpolation is using barycentric coordinates. Cool. Let's go into example. All right, sorry. So this is the code that Matt had for me from last lecture. So hopefully this is somewhat familiar. He created a sprite view controller as his root view controller. And the sprite view controller is a subclass of GLK view controller. He instantiates the context, sets it, and started loading the vertex shader as a string. And cleared the screen as green. So let's run this real quick, make sure we have what we see, expect what we see. So we should expect a green screen. All right, great. We have a green screen, and we're also printing out the contents of our vertex shader. Our vertex shader right now just sets a position of 0. Not very useful. So we want to go back and set up these values. We need to set up a vertex shader, a fragment shader, a program. We don't have a program. We need to compile our program. Our program is just a string right now. But to pass it to the GPU, we need to actually compile it so the GPU understands how to do that. We do that with by simply calling a compile method. All right, so I'm going to move this down. And so I have the string. Yes, I have the string, and I printed it out. I need to call compile. So the method is gl compile shader. Shader is an integer. I don't know what kind of integer it is. It's just an integer that represents the shader. But I don't have a shader, so I need to create the shader. I can call gl create shader. But shader takes an enum type. So this type is which type of shader? Is it a vertex shader or a fragment shader? So I'll start with a fragment shader. So create the shader. So OpenGL is a C library. We are not in C. We are not even a subset of C or superset of C, whichever one it is. So we have this intermediary. The intermediary is called something FFI, TTI, SSI, something like that. Some interoperability with Swift that is written. So we have these weird little things here. We have to create an enum for our GL fragment shader. Oops. GL fragment shader is an int32. GL create shader takes a GL enum, so we need to wrap those. A little annoyance just because of interacting with C. The upside is that you can still write your fragment shaders and your vertex shaders and port that over very easily. All you have to do is write the setup code around that and pass that to your GPU. But then you get the portability of your application. All right, so we have a vertex shader. We can create the vertex shader. We need to compile the shader. Easy, except we never gave it the source code. So there's a method that I should have, I don't remember. Shader source. GL shader source is where we upload the source code. And it takes the shader, takes the count, it takes an unsafe pointer, optional GL char. So in C, this is char star star. So this is an array of strings and a length. Don't remember the length is the array of lengths of each of those strings, because C strings don't have length unless you call strlen. Count is the number of shaders that you want to upload. You can pass multiple shader strings to a single shader if you want to, but that's more complicated than we need, so let's just upload one shader for now. And this takes an unsafe pointer of glchar. Glchar, I believe, is typedef to int8, or aliased. So we have a string. We need to turn that into raw bytes. So we can do vertex shader source C string using this string dot coding UTF-8 raw value. Vertex shader data. So vertex shader data is an unsafe pointer of int8, which is aliased as glchar. So I can pass this. I can pass the pointer value. Oh. This needs to be a var. When you deal with pointers, a lot of times it will make you use the var. And nil we don't need for some reason. Matt will probably explain why. Great. So we've uploaded a shader. Let's see. Here's our new things. We've created a shader. We've taken the raw bytes, defined a shader, uploaded the source, compiled it. Easy. But compile shader returns nothing. GL, it's a void method. It returns absolutely nothing. So we don't know when it fails. Working with OpenGL, you're dealing with the GPU, and you're offloading these programs to the GPU. And in doing so, it's very difficult to debug it. So it's kind of a weird, there's a lot of boilerplate code in here. So we do need to do a little bit of work to check if it A, succeeded, and B, get the log if it did fail. So I'm going to go back to my vertex shader. Oops. My vertex shader currently is valid. I'm just going to add a bug. This is a bug. Actually, it's not valid. There's no semicolon. Okay. So now I have a flawed vertex shader. And I want to make sure that it is invalid. And there's a method called shader get IV. GL shader get IV. And this returns a parameter from a shader object. So this is, we can ask for it for certain information. We'll be asking for a compile, there's a compile status. Compile status sounds good. Or shader type. Compile status is what we want. So let's go back and call our shader. Get the variable, get the parameter for the vertex shader. The parameter name, GL enum, is, I copy this, GL compile, GL compile status. Again, we're just wrapping that int value with an enum, and we need the parameter. So this is an out parameter. If you've dealt with out parameters in C#, it's a lot easier. In C, it's relatively simple. You just pass it the pointer. So it's asking for a mutable pointer to a GL int. The GL int is just our out parameter. So let's define GL int. Oops. And this is the vertex shader compile status. And it's, I'm just going to instantiate it as false. So when it compiles successfully, it will be set to true. I can pass it the pointer value with the ampersand. So I'm getting now the compile status, and I can just check it. So I'm going to do it. I'm just going to print out an error. And print out an error here. So compile the shader, get this compile status, use the out parameter, passing in the pointer to get the out parameter. Check if that status is false. If it's false, print out. If it's true, we're happy. So shader did not compile, as we expected, because we added that bug. But that's not really that useful. Binary response of whether the shader compiled or not. It's a lot of work to figure out where the bug is. So we can get a log, do it in a similar way. There's a method called GL shader get shader log. GL get shader info log. And we pass it the same shader. Vertex shader. Buffer size. Don't recall buffer sizes. I think it's just one. Oh, we can't get. Okay, I know. This is asking for the size of the C buffer, or the char buffer, where you're going to store the data. This actually does not make sense at all to me. Really, there's two things we need to get first. First thing we need to get is, oh, just one thing. We need to get another variable. Instead of GL compile status, we need to get GL info log length. We need another variable. So we can get the length of the log. This, I believe, is nil. This buff size is your log length. No, it can't be right. This length is nil. What is... You have to ask Matt about this? I'm not sure. But we do pass in the log length, which is how many bytes we're writing to our buffer. And this info log is our buffer of bytes. So we're going to create a buffer. And it's a type unsafe. Sure. No. Unsafe, mutable pointer of, just as they specified here, GL char. We're going to allocate log length. So we're going to allocate the number of bytes that we are told that the log is. And it's complaining because log length is a GL int, but it wants an integer. So pass an int. So we have a buffer. Pass in the buffer. This will write out those bytes to our buffer bytes, and we just print it out as a string. C-string, pass in the log buffer. All right, it's saying that this variable is never mutated, even though we're writing bytes there. But the variable holding the pointer never changes, so that can be a let. But other than that, simple enough. Conceptually, it's very simple. Compile the shader, check the status, get the log. But there's a lot of boilerplate code, and a lot of that is because it's a C library that we're interacting through Swift. I did not get anything back, which is unexpected. So my log length should be 0. My log length still 0. Interesting. Log length. Yes. Essentially, we haven't set the current context yet. Okay, so we were trying to compile a program, but we didn't have the context set. I believe that is the reasoning. All right. So now we have actual errors. This reserved word, this syntax error. And that's at line 0, position 2. Yes?
What is that?
Set context. Essentially, this is the core piece of it. EAGL context.setCurrent. I just split out context into a separate variable. So great. This is a reserved word. Or is this line 2? Line 2, position 0? I don't know. It's still a bit cryptic, but it's certainly better than a binary did compile, did not compile. So I'm just going to take it out for now, and hopefully everything should compile. Shader did not compile. I guess this is line 3, bracket, syntax error, syntax error. Very cryptic, but syntax 3, line 3, and look at the previous line, there's no semicolon. Great. Shader not compile, undefined identifier GL position. That is odd. Oh, well, that's embarrassing. I compiled the fragment shader, not the vertex shader. Which makes sense because positions don't make a little ton of sense for a vertex shader, or for a fragment shader. Fragments don't care where they are, necessarily. They just care about the values that are passed in, the interpolated values that are passed in. Still a green screen, but recompiled. Everyone's happy. So I'm just going to add a fatal error here. So when it ever fails to compile, we immediately break. And I'm going to change this. Oops. Okay, so same thing. The only thing is a fatal error, and no reason to print out compiled. Great. It's a lot of code to do absolutely nothing. Our screen is still green at the moment. Great, so we have our vertex shader. Let's do the same thing for our fragment shader. You could split this out into another function. It's probably better, but I'm just going to copy paste. So vertex shader becomes fragment shader. Vertex shader, should probably copy, search, replace. Great. So we compiled our vertex shader and our fragment shader. So if I go back to this, we also need to write a program. But we've essentially written our program. Our program is the combination of our vertex shader and our fragment shader. So we just need to combine those two into an actual program. Easy enough. It's a similar methodology. So we have our program. We have our shaders, our compiled shaders that have successfully compiled, because we're erroring out if they don't compile. Let's create a program. GL create program. Aptly named. So we add our shaders. GL attach shader. Attach takes two parameters, the program and the shader. These are just integers, so we use those same variables that we have. Attach the vertex shader. Attach the fragment shader. And then finally we have to link, just like linking your binary if you're writing a C program. Link that. But it's possible for this to link. If for example, we never attach a fragment shader or vertex shader, our program is useless and it causes an error. So we should check the link code. Just the same way we did it earlier. GL get program IV as opposed to GL get shader IV. Pass the program. Pass it a parameter name, which I'm not sure about. So I'm going to look it up. GL get program IV and check the Chronos reference. Oops. I'll just Google it. So this is OpenGL ES 2.0. Accepts delete status, link status, which sounds good. Validate status, log length, attach shaders, attributes, max length, blah, blah, blah. GL link status sounds great, whether link succeeded or not. So we pass GL enum with a link status, and we pass it the link status GL in pointer. Again, assume it's false until we're told otherwise. If link status equals, I'm just going to fatal error, program did not link. Getting the log is almost identical, so I'm going to copy paste that as well. So the difference, instead of getting the shader log length, I'm going to get the program log length. Instead of asking from the shader, ask it for the program. And then this reading from the buffer is exactly the same. GL get shader info log is now something else. GL get program info log. Perfect. And from the program, not the shader. Great. So I can make sure that worked. I just don't attach a fragment shader. I expect to get an error. Shader do not compile. Syntax error. Oh, this is my fragment shader. Fragment shader. My fragment shader just sets it to yellow, looks like. Great, so we know the fragment shader compiling code works. The program did not link. Exactly one vertex and one fragment shader to link. Perfect. Comment that back out, everything should be happy. Great, no errors. Everyone on board? No? Let me know where to scroll to. Right there. So compile the shaders, build the shaders, link the program, attach the shaders, link the program, and check status. A lot of boilerplate code. And this is the worst of the boilerplate code, so now we only get to work with actual data, which is fun, exciting. All right, so we have our program, we have our shader, we have the architecture, we have the building blocks. We actually need to pass it data. Right now, we just have a green screen. We're not drawing any geometry. So OpenGL works with very simple geometry. I think DirectX allows quads. I don't think OpenGL does allow quads. I'm not sure about that. But geometry is relatively simple. We can just define our geometry as vertices. So let's go ahead and do this. So down here we have our draw method. This is a lot like drawRect, but this is called, for you, this is called, this is your setup code sending data to the GPU. So all we want to do is send geometry, send any other info, draw. Simple steps. So attributes. So we have uniform variables and attribute arrays. Uniforms are the same for every single vertex or every single fragment. So these apply globally, whereas attributes are individualized data. This vertex is this position. for example. So let's define a triangle. Triangle is relatively simple, 3 points. Who wants to give me points for a triangle? Anyone have 5 and 6? All right, great. 12 and 0. -1 and can't do math. This is 0 as well. -2. And square brackets. So this clearly defines a triangle of some sort. Kind of imagine what it looks like, but not really. It's a kind of an odd shape. Okay, so this does define a triangle. So we just need to pass this information down to, or pass this information to OpenGL and our vertex shader. We do this by calling GL tribute trib pointer. So there's GL vertex. So you can pass it individual vertex, an individual number. Not that useful. Or you can pass it 2 float values. We're going to use GL vertex pointer. It makes more sense because you're passing usually a lot of data. If you have a big complicated geometry like cube is composed of 8 points, but you need to define it as a triangle, so you need to define slightly more than that. But we have a triangle. Size, this is not right. GL vertex trib pointer. Index. Index is how we associate this array of vertices. No, it's not true. Index is the index of our attribute. Size is how many points represent a vertex. So a vertex in 2D is 2 points. Vertex in 3D is 3 points, sometimes 4. So this is 2. Our triangles in 2D are 2 points. Type, we can use integer values or we can use float. So that's what this is asking for. GL float. Normalized, we pass in false for, I forget why, Matt will explain. GL Boolean. GL Boolean. Stride. Stride is how many bytes from the first vertex to the next vertex. It is possible to put in data in between. Maybe you want to convert. Maybe you have vertices of 4 points or 4 values, and you want just 2. You can just skip over some of the values. It can be useful if you want to encode additional information, say color information or normal information. You just want to jump over those. Depends on how your data is input. But if it's tightly packed, like this, where it's one vertex, another vertex, you can pass in 0, and it will jump the correct amount. The correct amount is GL float, which is 4 bytes. Floats, 32-bit floats are 4 bytes times 2, 8. So that's 8. So this 0 is equivalent to 8 based on our data, based on our inputs. And pointer is the position, is the pointer value to our data. Index, just a number to identify our attribute. Ideally, I mean, we can do something smart. We can have variables to associate this information. I'm just going to use 0 for now. 0 is simple. So I've sent my data to OpenGL, but hold on. How do we even know this is valid data? depends on what coordinate system OpenGL expects, right? This could be 1 pixel on our screen. This could be entirely off our screen. This could be an entire screen. So there is an importance to understand what OpenGL's coordinate system is. But in actuality, it may not matter at all. The reason is the vertex shader. The vertex shader operates on vertices. We can write our vertex shader in a way to transform our information, our geometry data, into OpenGL coordinates. Or we can just pass it in as OpenGL coordinates in the first place. I'm going to, I don't know if that tells you this or not, but OpenGL is -1 to 1, -1 to 1, x and y. So normalized in that way. So if your geometry is specified, depends on how you want to define your geometry. You have that choice, usually. Sometimes you have someone build you a model, and they give it to you in a certain format, and you don't have a choice. In that case, you can adjust your vertex shader to transform it in certain ways. Anyway, so we've uploaded our geometry, vertex pointer. So we've uploaded our geometry. The next thing we do is just draw that geometry. Easy. Mode. GL triangles. So there's different ways to draw. GL points just draws individual points. Lines, line loop, line strip. Line loop just, I think it just adds another point using the previous point, adds another point using the previous point, and it closes itself, I think. Line strip is just using the previous point. Triangles is you just give it 3 vertices, and that's your triangle, draws that. Triangle strip reuses the last 2 vertices, so you can just chain them very easily. Triangle fan, you just reuse the first one always as your center point. So these are kind of interesting. Triangles is the simplest to understand. You just pass it 3 vertices. If you want to add another triangle, you pass it 3 more vertices. So triangles is great. First is which vertex do we start with? If, say, we have a big vertex array and we just want to use part of those vertices, or part of those, a chunk, a subsection, we can do that if we want to very easily. But in this case, we'll just start at 0 and count. Count is not the number of triangles, but the number of vertices that we're drawing with. So 1 triangle is 3 vertices. 3 vertices. Don't need this ampersand because passing in a float array, smart enough to understand to pass in the pointer value. All right. Great. So we get nothing. No output, no nothing. So this 0 represents nothing. Doesn't mean anything, really. It's just a number right now. So what we want to do is we want to associate that number with our fragment shader, or vertex shader. Our vertex shader also draws everything at 0. We want to have a position. If I look back here, attribute arrays, yes. So we're passing in two floats. And so the attribute is a vec2, and we can name it whatever we want. Position. So this position we need to convert to OpenGL coordinates. And so we can just pass it the position pass it the x, the y, 0 for the z. We're 2D, so don't care about the z, and just using 1.0 for w. W usually is 1.0 unless you're dealing with some more complicated transforms and matrices or something like that. Matt, I'm sure can explain more. That's his area of expertise, so he knows a lot more about it than I do. All right, so we're uploading our position, but our program doesn't know what position is. It just knows to upload to position 0, which doesn't mean anything. So we need to tell the program what position 0 is. We can do that by calling gl bind attrib attribute location. We pass the program the index, which is 0 is what we defined. And we pass it the string name, position. Because we defined it in our shader as position, we bind it as position. Now whenever we use 0, it's treated as if it's position. So this is an optimization. Instead of trying to look up every single time the string position, we just look up 0. We know it's 0. And finally, we need to use enable. We need to enable that array, position 0. Great. Hopefully we see something. We see nothing at all, which is disheartening. And even if we debug it, it's very difficult to go through and see where the issue is. So in the end, you just have to play around with it. I'm going to change this triangle to start at 0, 0. 0, 0, 1, 0, 1, 1. Because I know OpenGL is normalized from -1 to 1. I can just pass in certain values. Or I could go to my fragment shader and try to adjust them so I see something. Still see nothing. Well, drop raise. Clear. Drawing triangles. So this is a valid triangle, yes? 0, 1, 0, 1, 1. Should be valid. Position. Okay. Arrays. Head shader. Bind attrib. Enable vertex trib array. I do not know. Trib pointer. Oh, GL vertex of trib pointer. I think that's it. Vertex of trib pointer. GL enable vertex trib array. Oh, got it. So I think you do need to start using the program. You need to say you're going to use the program. Building it and linking it doesn't necessarily do enough. Hey, there we go. It's a lot of weird little edge cases, so just be careful. So here we have this use program. Great. So we have our program, we have a triangle. Notice where positive x is. Positive x is to the right. Positive y, however, is upwards. Does that mess with everyone? It's used to positive y being down. Well, you just got to deal with it. It's one of those weird quirks, different coordinate systems. All right, so we have our triangle. We want to add another triangle. It's really easy. I want to add the other triangle, the corresponding triangle, to make my quad. So just copy paste. This is the exact same triangle. The difference is 0, 0, I have 1, 1. The only difference is 1, 0 should be, this one needs to be swapped. Sure. So I get nothing. I didn't tell it to draw 3 more triangles, or 3 more vertices, so draw 6. Perfect. I've got my quad. Is there a part you want to see in particular? All right. So this is setting up the context, setting the vertex shader. Set up the context. This is just pulling out the vertex shader from the file. Create the shader, specify as vertex shader. Upload the source, pass it just one source file, pass it the raw source data, compile it, and just check the status. Yes? I think so. Yes. I'll talk to Matt, maybe I can upload this. He usually doesn't like to upload code, but a lot of it's boilerplate, so I might just upload just the boilerplate stuff. Compile the shader, hit the log. This is the same thing as a fragment shader. The only difference is the fragment shader we created as a fragment shader rather than a vertex shader. So that's a lot of work to draw a square, or a rectangle actually, quad. Not that useful, but a lot of the powers we can do in the vertex shader. We can do more with that information. We can upload some more to it. So I want to move my fragment, my quad around. I want to bounce up and down. Sounds like fun. So what I'm going to do is add I'm going to adjust the position of my quad. So what I'm going to do is going to specify a translation. Translate X, translate Y. Oops. Make them private. So I can just adjust the position of every single fragment, or every single vertex at runtime. So I can go in here and say plus translate X plus translate Y, and already I'm getting bored. Do all this geometry change to my triangle. 6 different vertices with 2 different points each. That's 12 different floats I need to constantly update with this translation. There's no need to do that. I can upload it to the vertex shader. The vertex shader, it runs on the GPU. It can do all that math for me. So I can just adjust my vertex shader. So I'm going to do say Y. So every time I redraw, I'm just moving it. All right, so I could go in here and add all those translations here manually, but if I want to add another triangle, it's a bunch more work. If I want to add another triangle, it's a bunch more work. So instead, I just pass this translation straight to the vertex shader. The vertex shader just works on fragments. It just has to do it for each fragment. It's relatively simple. But the idea is that it's a uniform. It's the same for every single vertex. So I transform the entire quad, not just one triangle at a time. So to do that, I just define a uniform in my vertex shader. It's vector 2. Call it translation. Translate. Doesn't matter. Just like position, I need to link it up in my code at runtime. So I just add the translation. Okay. And go back to my view controller. Upload the same exact geometry. I just need to upload the uniforms. And there are these methods GL uniform. Super simple. This is 2 floats, or 2 ints. 2 floats is perfect. So I want to upload it to somewhere. Upload it to translate. Don't know what it is yet. So I upload translate X, translate Y. I just pass those values straight through to my uniform, my shader. But this translate, this this takes a location. Location, it wants the position of the uniform as an integer, which is not very useful to me. So I can call GL get uniform position, get uniform location. And I pass it the name, which was translate, and the program. Except program was defined up here, glint, and it's local. No problem. I just need to make that private, make that an instance variable. So I can just move that definition to the top. And great. So when I create a program, I override the default one, and now I can pass in the program and the translation. Great. So I'm translating every frame to the left and down, but faster to the left than down. So I expect to see some sloping angle. Awesome. Because I'm doing it with a uniform rather than updating my geometry, I'm far more efficient, especially with these giant models sometimes that are hundreds of thousands of vertices. This is far more efficient. It's far easier to work with. And so attributes are things that apply to individual vertices, whereas uniforms apply to all the vertices. If I want to do something interesting, I could do, instead of translation, do time. And I can mess with time and I mess with sine and cosine and get some nice waves if I wanted to. Whatever I want. So great. So we talked about today. We talked about mostly the vertex shader. We talked about building up, compiling the shaders. We talked about all that boilerplate, linking up the program, passing information to the shaders. We talked about attributes. We briefly talked about uniforms. Uniforms, again, affecting all items in the shader, whereas attributes are per vertex. And we looked at the vertex shader. I think we'll cut it there for now. Next lecture, we'll talk a bit more about the fragment shader and passing information between those two. Any questions? I'm happy to answer questions about this or about the lecture in general, or iOS in general. All right. If you have questions, come talk.